Now it's going to feel like we're going to change topics here for a moment. Let's define the cross product. The cross product of two vectors u and v that are in three-dimensional space, where u is equal to u1, u2, u3, and v is equal to v1, v2, v3, is defined as, so we have u, and then to notate a cross product, we use a cross kind of multiplication symbol. So u cross v is equal to the first component is u2v3 minus u3v2. The second component is negative, I'll write it this way, negative u1v3 minus u3v1. And the final component of our cross product is u1v2 minus u2v1. Okay? All right. So I want to point out a few things about this cross product, because this is pretty different than our dot product. First off, this looks pretty gnarly, right? This is a gnarly formula to remember. Now, in just a moment, I'll show you a little bit easier way to remember it. But there's a lot going on here, okay? But there's some more interesting stuff going on other than just how complicated the formula is. Notice u and v, they can't just be any two vectors. They have to be vectors in three-dimensional space. The cross product is only properly defined in three-dimensional space. That's very different than the dot product, where you could take the dot product of any two vectors in any number of dimensions, right? The cross product only is defined, only properly works in three-dimensional space. So you have vectors in two-dimensional space or five-dimensional space, cross product isn't defined, okay? And finally, the last thing that I'm going to notate, big difference from the dot product. The output of a cross product is a vector. Remember, when you take the dot product of two vectors, you got a scalar when you were done. But the output of a cross product, if you take the cross product of two vectors, you get another vector. And that's pretty different, okay? Now, I'm going to write this in a slightly different way, and it might make us think of something, okay? So I'm going to write this in terms of the standard unit vectors as a linear combination of those I, j, k vectors. So I'd get u2v3 minus u3v2, that's the first component, times the standard unit vector I, minus u1v3 minus u3v1 times the standard unit vector j, since it's the second component. And now the third component of the vector, u1v2 minus u2v1 times the standard unit vector k. Now, if you were paying attention to what we were doing before, this should look familiar. It looks a whole lot like the formula for a 3x3 determinant, right? And in fact, it has that structure to it. And so this is how we're going to generally remember how to calculate the cross product. The ijk, they act as the first row of the matrix we're taking the determinant of. Vector u, the components of vector u are the second row of the matrix we're taking the determinant of, and the components of vector v are the third row. Of the matrix we're taking the determinant of. Okay? And so if you take the determinant of this, you will get this. You'll get the cross product when you're done. And this is much easier to remember. Okay, so when we're taking a cross product, this is what we will do to actually evaluate the cross product rather than trying to remember this complicated formula. All right? I do want to point out we're treating this like we're taking the determinant of a matrix, but it's a mnemonic device. It's not a true matrix because the components of a matrix have to be numbers. They have to be scalar values. And for all of these values, they are. But these are vectors. You cannot put vectors as the components of a matrix. So we're kind of abusing the notation here to get a mnemonic device to help us remember how to take a cross product. So it's not a true matrix, it's not a true determinant, but the rules for taking a determinant can be used here to help us remember how to take a cross product.